Good morning, my YouTube viewers. It is Crystal here. I'm just here because I want to do a code review, and I'm going to do code review based on an academic paper that was written. The title of the academic paper is Efficient and Adaptive Linear Regression in Semi-supervised Settings. So this is the research paper. It was written by Abhishek Chakrabarty and Tianzi K in the University of Pennsylvania and Harvard University. And it was copyrighted by the Institute of Mathematical Statistics in 2018. And so what it does is it talks about semi-supervised learning and linear regression. So that's the paper. You can get it on the internet, and I've got it up on the screen so you can either do a search on the title or you can type up the web address that's typed up at the top of the screen. So there's two ways that you can get this research paper if you want to look at it. I had a look at the research paper, and what I will say is it was written by people a lot more educated than I am, and so they were using complex mathematical formulas. And the last time I studied calculus was, well, over 40 years ago. We'll just put it that way. Over 40 years ago was the last time I studied calculus. So in order for me to understand all of the mathematical terminology in this paper, I would have to study calculus again, okay? But I have lots of demands of my time, so I don't know when I'm going to get around to studying calculus again and studying advanced math again. So now what we're going to do is we're going to go over to the code, which is while you're watching this video, I assume. And you can see in this code, excuse me, I've got the link to the paper, so you can get the link to the paper that way as well. So what we're going to do is we're going to do a semi-supervised regression with linear regression on sklearn's toy dataset diabetes. And the reason why I decided to use sklearn's toy dataset is because it doesn't need to have anything done to it. It doesn't need any data cleaning or anything like that, because what we're doing is we're talking about semi-supervised learning, and we're not talking about data cleaning. So, and also I don't have to provide you with a link to the CSV file either. So you've got your link to the research paper if you want to read it. I would highly recommend that you read a little bit of it, at least the introduction, so you can find out a little bit about semi-supervised learning and linear regression. And then so what I did was I created this library in Google Colab. Google Colab is a fantastic program to use if you want to undertake data science projects. But one thing that I will say about Google Colab is the fact that it does not have a good undo function. So if you accidentally overwrite or delete any code, then there's the possibility that you could lose it forever. But you can actually go into the save history of the program and try to retrieve it that way if it was saved in the past. So after we've created the program, then what we're going to do is we're going to insert our libraries. We're going to import our libraries. So we're going to import pandas as PD, which is your data processing library, and it creates data frames. We're going to import NumPy as MP, which carries out numerical computation, and it creates NumPy arrays. We're going to import matplotlib.pyplot as PLT, which is graphics library. We're going to import Seaborn as SNS, which is another graphics library, and we're going to import the warnings. So I imported the warnings, but I forgot to put the code in about ignoring the warnings. So if I need to ignore the warnings, I'll have to go into Stack Overflow and find the piece of code that I need to actually ignore the warnings. So I didn't do that. So that was an error that I made, because I really didn't want to ignore the warnings. What I wanted to do is, if there were warnings, I wanted to ignore them, but if there weren't warnings, I didn't want to ignore them. So after we import our libraries, we're going to load the dataset. So we're going to load the dataset from sklearn.dataset, and we're going to get the diabetes dataset. And data equals load diabetes as frame. So what that does is that's going to give you the dataset in frame format. X is going to be data.data, Y is going to be data.target, and then you get your X shape and your Y shape. Your X shape is 442 rows by 10 columns, and your Y shape is just 442 rows by 1 column. Okay, now what we're going to do is we're going to take the data set that has been created, and df equals X, df target equals Y, and then we're going to shuffle the data set. So df equals df.sample brackets, frac equals 1, that's for 100%, comma, random state equals 42 brackets. Then you're going to see the df, and you can see that it's been shuffled, which is what we want. Now what we're going to do is we're going to analyze the target. So this is a hist plot of the target, and so you can see the general distribution of it. And now we're going to make a few box plots. We're going to do a box plot for the age and the target. So here's your, you can see the box plot with the age and the target. You can see the box plot with the BMI and the target. So you can see that the higher the BMI, the higher the readings on the box plot are going to be. And you can see a box plot of the blood pressure and the target as well. So after we've done that, what we're going to do is we're going to define our dependent and independent variables. So Y is your dependent variable, and it's going to be the last column of the data set. It's Y equals df.iplot, brackets, colon, comma, -1, brackets. And then so the first colon means rows, and then the -1 means columns. So if you say -1, that means it's your last column. And then X is your independent variable. So X equals df.iplot, square brackets, colon, comma, colon, -1, square brackets. So what that means is it's taking all of the rows except for the last, all of the columns except for the last one. So the first colon is your rows, the second colon is your columns, and then the -1 means it's taking all of the columns except for the last one. And then you check your shape, so you've got 442 rows by 10 columns and 442 rows by 1 column. So that's what we had. We had the same number of rows and columns again. So now what we're going to do is we're going to create a 2D array of what the diabetes data set looks like in memory. And that's it in memory. Looks quite odd, doesn't it? And now we're going to do a 3D array of what the diabetes data set looks like in memory. And that's it in memory. So we're not going to normalize it. but I left the code to normalize it in there. The reason why we're not going to normalize it is because you don't have to normalize your data when you're dealing with linear regression. So we're going to split the df. So xtrain, so we're going to use sklearn to split the data frame. Xtrain, xtest, ytrain, ytest equals train test split, x, y. Test size equals 3. Random state equals 42. Xtrain dot shape, ytrain dot shape, xtest dot shape, ytest dot shape. So you can check the shapes of these. So the train is 309 rows and the test is 133 rows. Now what we're going to do is we're going to define the unlabeled data. Xtrain, x unlabeled, ytrain, y unlabeled equals train test split, xtrain, ytrain, test size equals 0.7, random state equals 42, and then you've got xtrain shape, x unlabeled shape, ytrain shape, y unlabeled shape. So you can see that the train size is 92 and the unlabeled size is 217. Now we're going to select our model. Our model is going to be linear regression. So REG equals linear, and we're going to use sklearn's linear regression. So REG equals linear regression, brackets, dot fit, xtrain, ytrain, and then we're going to print our score, and we get only 48% accuracy because this is a regression problem. And then we're going to predict on the unlabeled data. Label equals reg.predict x unlabeled, and you're going to print the score, and it's only 43% accuracy. Now we're going to print our labels, so we see we printed all the labels. Now we're going to check our RMSE, that's root mean squared error. Your RMSE is 56.61%, or 56.61. And now we're going to visualize the data. So you can see that that is the visualized data. So now we're going to compare the true values to the predicted values. So you can see the true values and you can see what the predictions are. Now what we're going to do is we're going to compare supervised learning to semi-supervised learning. So ypred equals reg.predict x test. We're going to check the error, and our error is only 50.4. And we're going to do a visualization of it. And then we're going to compare our true values with the predicted values. So you can see that when it's supervised, you get an error of 50, but when it's unsupervised, you get an error of 56. So supervised training obviously performs better than semi-supervised training, but it's very costly to obtain the labels for all the data, and that's one of the reasons why what they will do is they will label some of the data and leave the rest of the data unlabeled and hope for the best. But what I wanted to do, I set a test size of 0.3. I'm going to change this to test size of 0.1, and I'm going to rerun it, and I'm going to see what happens when we rerun it. So those box plots take a little bit of time to run up. So we had our test size of 10%, and so we had a 44% accuracy and 39% accuracy on unlabeled data. had an RMSE of 58. So that made it worse. And on this one, we had an RMSE of 50. So if you have, if your test set was smaller, which is what we did, our test set was smaller, then that meant that our RMSE on the semi-supervised data was greater. And the reason why is because you had more unlabeled data to look at. But normally when I do my modules, I normally have a test size of 10% and everything else is my training data. So when I decreased the test size, it did not have any effect on the supervised learning, but it increased the RMSE or the error on the semi-supervised learning. But I just wanted to see what would happen when I did that. So I think this concludes our presentation on semi-supervised regression problem with sklearn's diabetes dataset. This is something that you can practice on your own because it's one of sklearn's toy datasets. One thing that I found when I was studying semi-supervised learning is sklearn does not have any functions for regressions. sklearn has functions for classifications, but they don't have any functions for regressions. So I had to do some research to find that there is some semi-supervised learning for regression, but it's just not in sklearn. But I wanted to include it because I thought it was pertinent. So I'm going to go ahead and close this video because I've covered all of the points that I want to cover. And I would like to thank all of my subscribers for supporting my channel. If you like my videos, please like, subscribe, and share. Thank you very much for watching my video, and I look forward to making more code review videos for you in the future.